All right. This is just some real quick going over different ways to do electron configuration. Again, I would recommend that you try to do these problems on your own on a sheet of paper before before you actually watch the video answers and all. So if we're going to go ahead and look at the first one where it says write the electron configurations for the following elements. Use the periodic table as a guide. Number 12 and number 15, these are just different ones that I pulled off of different worksheets. Again, you don't have to have the worksheet in front of you. You can do this on a sheet of paper, and that will be fine. So again, we're looking for electron configuration. That's going to be regular order. Or standard configuration. If you want to pause right now, try to do number 12 and number 15, and then you can play the video to see the answers. All right, so first thing I do when I'm doing these is I go ahead and I find the element on the periodic table, and what I find is that copper ends up in the 3D box, 3D section of the periodic table. So I go ahead and write out my configuration without any numbers of electrons yet. I'll go ahead and write it out. So I have 1s2, 2s2, 1s, 2s, 2p, 3s, 3p, 4s, 3d. All right, that takes care of that. Now, from there, I just go ahead and fill in the maximum number. Remember that s orbitals can hold 2, so if they're full, they're going to have 2. A p can hold 6, and again, an s will hold 2, a p will hold 6, and then this s will hold 2. And then from there, we just count how many spaces it is into the d. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9. So copper is going to be 3d9. All right. All right. And one of the things before I move on this, I want to show you a way to check this. So if you look at copper on the periodic table, copper has 29 total electrons. So if we go 2 plus 2 plus 6, that's 10, 12, 18, 20, and then 9 more is 29. So it should total the number of electrons that is available for the numbers that we're writing as exponents next to the letters. They're not really exponents, but the numbers that we're writing there, if we add them up, should equal the number of electrons. All right, going to potassium. Again, we find that potassium ends up on the fourth period. It's in the S box. So I'm going to go ahead and fill in that, assume that the ones before it are full. So it's 1s2. Remember, s orbitals hold 2, p orbital holds 6. So 6, 2, 6. And then potassium is in the first column of the s orbital, so it is 4s1. And again, potassium has 19 electrons, so 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus another 6 is 18, plus 1 is 19. So we ended up with 19 electrons. All right, now, when we look a little further down here on this page, so now for these, the difference is all of these are ions. So what changes about an ion? Remember that a cation, which is positive, loses electrons. And then an anion, which is negative, has gained electrons. Ah, that was horrible. All right. So when we're looking at these for aluminum, um, again, we're going to be losing 3 electrons. So what I'm going to do is I would go ahead and write out my standard configuration for aluminum. I'm going to do aluminum for you and then let you try the rest on your own. So aluminum is in the 3p block. So that means I have a 1s, 2s, 2p, 3s, 3p. So all of these are going to be full. So that's 2, 2, 6, 2, and 1. Now, this is for a neutral aluminum. If I want to make an aluminum ion, I need to get rid of 3 electrons. So that means that I have 1 electron here, 1 electron here. So that's 2 electrons. Well, 1 plus 2 is 3, so that's 3. I'm going to remove the outermost electrons. So that means that for aluminum plus 3, my electron configuration is 1s2, 2s2, 2p6, which is isoelectric. This is another term that you're going to hear, is isoelectronic, which means it looks the same as neon. So if we were to do the electron configuration from neon, we would find that neon is also 1s2, 2s2, 2p6. All right. So isoelectronic means that the electronic configuration is the same. You can have another one that would be the same is the electron configuration for a fluorine ion, F minus 1.
I don't know that.
Fluorine ion would be the same electron configuration. All right, so what I would like for you to do is go ahead and try to do chlorine ion, magnesium ion, and a nitrogen ion as well. So pause the video right here, and then when you have attempted these, go ahead, restart the video and see what you come up with, and see if you come up with what you come up with matches mine. All right, so here are your answers for the ions remaining, chlorine minus 1. All right, so we can see chlorine's normal electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p5. But we add 1 electron, so that makes it 3p6. So it becomes isoelectronic to argon. For magnesium, we are losing 2 electrons. So magnesium is actually in the 3rd period. So it should have ended with 3s2. But we lost those 2 electrons, so that makes it 1s2, 2s2, 2p6, which is the same, or isoelectronic, to the aluminum plus 3 ion. And it's also isoelectronic to neon. And then what we find out as well is nitrogen, a nitrogen ion, N minus 3, is 1s2, 2s2, 2p6 as well, because it gained 3 electrons. So going from 2p3 to 2p6, and we find out that it is isoelectronic to aluminum plus 3, neon, and magnesium plus 2. That they all look the same as far as the electron configuration. All right, so again, go ahead and do number 32. This is just another one that's an ion. Strontium's just a little bit further down on the periodic table, and you can see some things that change. So again, I'll just kind of show you this one as if we were doing it together. Hopefully you paused and tried to work it first. I'm going to show you how this one is different from the neutral. I'm going to do the neutral first and then show you how it changes into the green. So remember, everything on the inner shell, or the core electrons, are full. So 2, 2, 6, 2, 6, 2, 10, 6. All right, so these would represent my core electrons. That's going to show up in your homework questions on Chem 101. All right, so in this case, strontium has 38 total electrons. 2 of them are going to be valence, and so that means that there are 36 core electrons. And just kind of going through and checking the math, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, 18, 18, 20, 30, 36, and there's our 36. Sorry, I had to clear my voice. Now, this is for neutral. Remember, I'm doing the neutral first. So a neutral atom of strontium would have 38 total electrons. And if you see, strontium, Sr, is in the second column of the fifth row, so that means it's 5s2. Now, right here, we are getting rid of 2 electrons. So this is what we get rid of, and that's the change. This is how it's different. So this, our core electrons, now becomes our ion configuration. So remember, whenever you're doing electron configuration for an ion, you just change the, you just either add or remove electrons from the total, depending on if it's positive or negative. If it's positive, you lose electrons. If it's negative, you gain electrons. All right, just another one, just real quick. I want us to do Lewis dot structures. For these, remember, Lewis dot structure is only the valence electrons, which is the outer shell. Or the outermost electrons. So we are only looking for the s and p orbitals for these. So what's on the total thing? There's a couple of different ways you can approach this. You can look at the column that it's in. So for example, oxygen is in family 16 or family 6A. So that means it has 6 valence electrons. So 1, 2, 3, 4, 5, 6. Fluorine is in column 7A, so 1, 2, 3, 4, 5, 6, 7. And I'm also kind of showing you correct fill order. Carbon is in column 4A, so that means it's going to have 1, 2, 3, 4. And then go ahead, pause it, try the last 3 on your own. All right, so going through these, neon is a noble gas. Noble gas has a full octet. That's why it's considered to be stable. So it already has 8 electrons around it. Iodine is in column 7A, has 7 electrons. And then potassium is in group 1A, or group 1, so it has 1 electron. Moving on, your homework is going to ask you questions talking about ground state versus excited state. So I kind of wanted to give you these notes so that you can see. You can write these down or just come back to the video when you need it. When all electrons in an atom occupy the lowest available orbitals, or the lowest energy state, then when that happens, it's considered to be ground state. When an electron absorbs energy, they have the ability to jump to higher energy levels. When they absorb energy, they become excited, meaning that the electrons have absorbed energy and they move, or they jump to a higher energy level. So for example, it might, for hydrogen has 1 electron, and it's in 1. All right. And let's just, even though there's no electrons in these orbitals exist. So I feed in some energy, and I give that electron some energy. And when I give that electron some energy, it jumps to a higher level. So now that electron has moved from N1 to N3. And so it's gained that much energy. And then it'll go around there for a little while, and then as it goes around there for a little while, it's going to lose some energy, and when it loses that energy, it'll drop back down to its normal state. So here it's excited, here it's ground. Just kind of wanted to go through that and check on that. Now, so another way that we kind of show this, just kind of remember that when an electron jumps to a higher level, it absorbs energy, or it absorbs energy and jumps to a higher level. Excited state is temporary. It will stay there as long as the energy remains. Once the energy is lost, the electron can drop back down. All right, so it's going to absorb energy here, and then here it will emit or release energy. All right, so what we're going to be looking at in this is sometimes it'll ask questions about which one releases the most energy or absorbs the most energy. So we have this equation called the Rydberg equation. R-H-Y-D-B-E-R-G. Rydberg equation. And we don't have to completely solve this equation, so we don't need to know all of the information. But what it basically, the equation is basically delta E, which is change in energy, and we'll go from initial minus final, or initial to final, sorry, is equal to R, and R is a constant. But I don't need you to know this number right now. You don't need to know the number for R. We're just going to use it and assume that it's a constant. It's always the same. So it's always going to be multiplied the same. So if we just solve solve this next part of the equation is all you really have to do to know what the change in energy is to be able to compare. So, so it's going to be R R times 1 over N, which is your quantum level, squared, final, minus 1 over your quantum level initial, so your original quantum level squared, 1 over your initial quantum level squared, and so on. So we're going to do a question that you have to do this and one that you don't. And then I'm going to show you a way that you don't really have to use the equation to get it. You can just kind of see. But and so there's a couple of different ways you can approach these questions. So let's move forward a little bit and check this out. All right. So let me pause just. Okay. So a couple of different ways that these questions will be asked about this. You might see a couple of these in your homework. It just kind of depends which one you draw to get this. So it says electrons in the fourth energy level of an excited atom will emit photons. So we have an electron in the fourth energy level that will emit photons as they fall to lower energy levels. Using the image below, how many different electron transitions are possible? Okay, so we could move from N1 to from N4 to N3, so that would be one possible one. We could move from there to there. That's another possible one. We could move from here to here. So that's 3 possible ways. Now, you could also, since you have an electron now on this level, you could move from here to here, so that would be 4, or you could move from here to here, that would be 5. And then the other possibility would be the electron that you have here could be 6. So there are actually 6 possible transitions that could be made. So we could actually see 6 different colors or 6 different flashes of light as this is happening. And that's one possible way to answer this question. Now, I'm going to pull it down and I'm going to show you a different question. And there's actually 2 ways that we can answer this question. So it says in a Bohr model of the hydrogen atom, the energy required to excite the electron from N2 to N3 is blank than the energy required to excite the electron from N3 to N4. So here we have the Rydberg equation, and what we really need to do is, again, remember R is a constant. We don't really have to know that one. But setting this up, so we have change in energy. We're going to have to do this twice. So we have change in energy from 2 to 3 is equal to R times 1 over 3 squared minus 1 over 2 squared. And then we solve that problem. Basically, all I really want to know is that it's going to be, the answer is going to be negative 0.14R. All right, is my answer. Now, if I come down and I look at, I want to compare this number to what I get for this one. So I'm going to give myself a little more room. And so delta E from 3 to 4 equals R times 1 over 4 squared minus 1 over 3 squared. And so when we solve this one, we end up with a negative 0.05 R. So which of these numbers is greater? Well, 1.4 is greater than 0.5. So what we can say is that the change in energy from 2 to 3 is greater than the change in energy from 3 to 4. All right, so it's greater than. All right, so another way to approach this question, and you can use that little diagram that I had up here. So we have, and I'm going to do this one in purple, and you see how the lines from 1 to 2, you have a bigger jump than any of the other ones, and so like the lines get progressively close together. That's what actually happens in an atom as well when you're adding energy levels. So if we have an electron that goes from 2 to 3, and this is our change in energy right here, and then we had another electron, and let's use red for 3 to 4. All right, so we had an electron that was on 3, and it goes to 4, and that's another change in energy. You can really just use relative size. Which arrow is longer? The arrow. So in this one, which arrow is longer? Or are they the same size, or what? In this case, from 2 to 3 is greater than 3 to 4. And you can see it relative like that. So you can do it using the Rydberg equation and just solving for whatever times R. This is always going to be right. Again, this one you have to remember the trend that it takes more energy here than it does here and it does here. So this is the largest amount of energy. And then this one would be medium. And then this one would be small. And then also recognize that we could have said 1 to 3 versus 2 to 3, or 1 to 3 versus 2 to 4, and you still have to recognize that size change, that 1 to 3 is going to be greater than 2 to 4. That's why I said the Rydberg equation will always work. It does that for you. You don't have to lay the lines next to each other or anything like that. All right, so that kind of concludes the lesson today. You should be able to, and let me pull it up and get out of that. You should be able to answer questions all the way up to number 24 on the on Chem 101. So your homework tonight is to answer questions in Chem 101 homework 9, basically questions 1 through 24. All right, Remember, I still haven't I haven't went over question 7 yet, so you can omit or skip number 7. I'm going to handle that one at the end of the unit. It's not that big of a deal on that question. And I'll have to, it's actually some extra information that we don't really need to know. I may just give you that answer, just depending on how much I see that we need to know that answer. That answer will not ever be, that question will never be tested. It's just an extra piece of information that you need to know. I'll probably link a Khan Academy video, but I'm thinking I'm just going to give you the answer for that question. All right. If you have questions, please post them in the comments of Google Classroom or email me, and I will respond to those questions.